Morning. In the last video, we started talking about the light-dependent reactions that cannot occur without the presence of light, and where the photons obtained from light energy are essential to trigger the whole process. And we said that the products of the light-dependent reactions are ATP and reduced NADP, and that both of them are utilized in the next important step, which is the Kelvin cycle or the light-dependent reactions. We also said that there are two pathways for the light-dependent reactions. The one that occurs most of the time, that is the non-cyclic phosphorylation, which occurs in a rather linear pattern, and the cyclic phosphorylation. We will start by the non-cyclic phosphorylation, and we already started last time when we talked about chemiosmosis and the diffusion of hydrogen ions along or down concentration gradient, and how this will serve in the formation of ATP molecules. But this time we're going to start by the diagram, because the diagram will show you details that will help you understand more how non-cyclic phosphorylation occurs and how it ends by the formation of not only ATP, but ATP and reduced NADP. It's worth reminding you of what we have said last time, that we have two photosystems. Each photosystem consists of pigments and electron carriers, and that photosystem 2 works first, and that the product of photosystem 2 is ATP, and then the electrons from photosystem 2 will be received by photosystem 1 that was discovered first, but that acts next, and this is very important. And at the end of photosystem 2, which also consists of pigments whose center is chlorophyll A and electron carriers, at the end of photosystem 1, we will obtain reduced NADP. Let's look at the diagram. Here we start. This is, of course, a diagram that shows you non-cyclic phosphorylation, and that shows you how photosystem 2 acts first, followed by photosystem 1 to give the products of the light-dependent reactions. Now, let's start here. Let's start by the exposure to the photons of the solar light energy. These photons fall onto photosystem 2. So this green structure represents what? It represents the pigments in photosystem 2. And as you know, photosystem 2 and any photosystem consists of a group of accessory pigments, and those accessory pigments receive the photons from light energy. And those accessory pigments have an absorption spectrum that is different from that of chlorophyll A. So each one of them absorbs maximally at a wavelength that is different from chlorophyll A, and this is what we have seen in this diagram. So there was a diagram like this one that shows you how the accessory pigments have different absorption spectra, meaning that lutein, for example, absorbs maximally at 470 nanometer wavelength, whereas zeaxanthin and other pigments have different wavelengths that they absorb maximally. Is this important? Yes, because the presence of the accessory pigments allows chlorophyll, or allows the photosystem to absorb wavelengths of different values. And this broadens the spectrum of energy that the reaction center can absorb. Why? Because these accessory pigments will finally transfer their energy to the reaction center, the center of the pigments and the center of the light-dependent reactions, which is actually chlorophyll A. And by the way, chlorophyll A is the central molecule in both photosystems 2 and photosystem 1. If you take the average, why do we call this photosystem 2? We said it before, because although it acts first in that series of biochemical reactions, yet it was discovered second. So the number 2 refers to when it was discovered. It was discovered after photosystem 1, although actually on the thylakoid membrane, it acts first. The second nomenclature we give to photosystem 2 is photosystem 680. What does 680 refer to? It refers to the wavelength absorbed by that photosystem. But we should say the average wavelength. Why? Because every accessory pigment absorbs a wavelength that is different from the other. So the average that we calculate by adding the wavelengths of each type of pigments and dividing it by the number of pigments, but we have to take into consideration that we should that these pigments are not present in equal masses inside the photosystem, so they have their relative weights or their relative masses. And this explains why, although photosystem 2 consists of the same pigments, yet the average of photosystem, although photosystem 1 has the same accessory pigments as photosystem 2, yet we call it photosystem 700, which means that the average of wavelengths that are absorbed by that photosystem is 700, and which means you might be wondering why they are different. This is because of what I have just said, that although they have the same pigments like lutein, like zeaxanthin, like beta-carotene, that have the same absorption spectra everywhere, but they are present in different concentrations or in different relative weights. Anyways, the photons have their energy and they fall onto the chlorophyll molecule. So the accessory pigments will funnel the energy they absorbed onto chlorophyll A. So chlorophyll A will receive concentrated energy, and with a very broad spectrum of wavelengths. And therefore, if you have a broad spectrum, if you can absorb or if you receive a broad spectrum of wavelengths, then you can receive a higher amount of energy that will be focused or funneled onto you. How do the accessory pigments send their energy to chlorophyll A? Either by radiation that does not require matter or by convection. Both methods of transfer of energy have been studied in the middle school. Now, when these photons fall onto the accessory pigments and then are funneled onto chlorophyll, what happens, as we said before, is that the reaction center, chlorophyll, will be activated. And actually, the magnesium atom that is surrounded by double bonds everywhere in the center of the chlorophyll molecule will be excited. And this excitation, if it has received enough energy, then it will lose an electron. And in such a case, we will have what we call an electron hole inside the whole chlorophyll molecule. Means that an electron hole simply means that there is a missing electron. Why is there a missing electron? Because that electron has escaped the molecule. But in order to prevent that electron from turning back to the chlorophyll molecule, it will be received by a series of electron carriers. As you can see here, we have, for example, plastoquinone and other electron carriers that you might be seeing in detail on other diagrams later on. And as we said before, these electron carriers, we might draw them here. For example, if this is electron carrier 1, this is electron carrier 2, this is electron carrier 3, they transmit the activated electron from one carrier to another. So that's why we call them electron carriers. But as I said before, they are not only electron carriers, they have other properties. First of all, they are integral proteins of the cell membrane. So they are 3D proteins that lie in the cell membrane. Number two, they transfer the electrons or carry the electrons at gradually decreasing energy levels, which means that if electron carrier 1 receives the electron at energy level 5, so 2 will receive it at energy level 4, and 3 will receive it at a lower orbit or a lower energy level 3. And every time the electron goes down an energy level, energy will be released. And it is all this, or part of this energy, that is released from the transfer of electrons that will be stored as ATP. That's why we say that at the end of the electron transport chain so we have the reaction center, which contains chlorophyll A, and that reaction center will be activated and will give its electron to the electron transfer chain. And then at the end of this electron transfer chain of photosystem 2, we will have enough energy to form ATP molecules. But notice that these electron carriers are not only proteins that carry electrons at gradually decreasing levels, but they are also proton pumpers. So part of the energy, as we said, has been stored to generate ATP molecules, but the rest of that energy is utilized to pump protons. Protons are hydrogen ions, and once I utilize the term pump, this simply means that we are talking about active transport. So actually, what happens is that the protons are being pumped all the time by these electron carriers from the stroma of the chloroplast to the inside of the thylakoid, or to the thylakoid lumen, which means that there will be accumulation of protons against their concentration gradient in the thylakoid lumen, and this explains the acidic pH inside the thylakoid lumen. And needless to say, as I said before, when I talked about the question that comes frequently on the test, what happens if you prevent pumping of protons using a chemical, for example, that blocks these these proton pumpers? If you block pumping of protons, you wouldn't have accumulation of protons inside the thylakoid lumen, and therefore you wouldn't have an acidic pH. You would have a less acidic pH, maybe neutral or even alkaline. And then what happens afterwards, or before saying what happens afterwards, we should focus on or we should highlight two important facts: that the transfer of electrons along the electron transfer chain generates energy, and that part of this energy will be used for proton pumping. Part of this energy will be used for proton pumping, and part of this energy will be stored as ATP. This is the first piece of information I would like to highlight. The second piece of information is the source of the hydrogen ions inside the thylakoid lumen, and that makes the thylakoid lumen acidic. We have two sources for the protons or hydrogen ions inside the thylakoid lumen. We have proton pumping, the pumping of the protons and photolysis. Why photolysis? Because the water that lies inside the thylakoid lumen undergoes splitting into hydrogen, as we said before, and oxygen per water molecule, and then these hydrogens will be dissociated into 2 protons plus 2 electrons. So photolysis of water is another source of hydrogen ions. So again, the energy released from electron transfer is partly used for proton pumping by the electron carriers, which are also considered proton pumpers, and it is partly stored inside the ATP molecules to generate ATP molecules at the end of that electron transfer chain of photosystem 2. And then, as we said before, these electrons of resulting from photolysis of water will do what? They will replace the electron or fill in the electron hole that lies inside the chlorophyll molecule after it has been activated. And now we come to the other photosystem, which is photosystem 2. Photosystem 2 receives light at the same time as photosystem 1. This one, photosystem 1, receives light at the same time as photosystem 2. But why then do we say that it acts next to or following photosystem 2 if solar energy falls onto them at the same time or in parallel? It's just because photosystem 1 that begins after the electron transport chain of photosystem 2 has to wait for electrons from the previous photosystem to fill in the hole. Meaning what? Meaning that it's true that light falls onto the 2 photosystems at the same time. And it is true that photosystem 1 will also lose an electron upon being activated. But this time, the electron hole inside the reaction center or chlorophyll A of photosystem 1 will not be replaced by electrons from water. And this is an important difference between the 2 photosystems we have talked about before, but it will be filled in by the electrons that are transferred at the end of the electron transfer chain of the previous photosystem. So this is an important difference between the 2 photosystems. And then the electrons will be transferred along an electron transfer chain that contains a very important electron carrier. Here we said that the very important electron carrier is PQ or plastoquinone. Plastoquinone. This is a protein in the cell membrane that acts as an electron carrier, that acts as so it is a protein, a cell membrane protein. This is the first characteristic, membrane protein. It's also an electron carrier. It's also a proton pumper. See how many characteristics it has. And it's also having enzymatic activities, and therefore it acts as an enzyme. Here we have another cell membrane protein, which is ferredoxin. So the most important electron transport protein here is ferredoxin. That is also an integral protein of the cell membrane that acts as an electron carrier, that acts as a proton pumper, and that has that helps at the end of the electron transfer chain to form reduced NADP. So these electron carriers, as we said, also have enzymatic activities, and NADP is one form of the enzymes or one example of the enzymes. NADP is a hydrogen carrier, so NADP carries the protons and is converted into reduced NADP. So we can obtain reduced NADP at the end of the second electron transport chain, which is that of photosystem 1. What happens afterwards is something very important, which is the presence of this very special molecule that is called the ATP synthase. As its name indicates, ATP synthase is an enzyme that catalyzes the synthesis of ATP. And as you know previously, all enzymes are protein in nature. And as you can see on the picture, it is a cell membrane protein. And it has a very specific shape. It is bulb-shaped on the side of the chloroplast stroma. It looks like a bulb, okay? But at the same time, it can rotate, okay? So how can it generate ATP? Actually, let's go back for a while. We have just said that at the end of photosystem 2, we use the energy to store it to form ATP molecules. It's here that the ATP synthase acts. So actually, this energy that is released from the transfer of electrons along photosystem 2 is not directly stored inside ATP. And this is very important. We have said this just to remind you that at the end of photosystem 2 electron transport chain, ATP molecules are generated. But what happens actually is that we have a series of electron carriers. And these electron carriers are pumping protons inside. So this energy has been stored inside the protons. And then after having pumped a lot of protons, we now have a higher proton concentration inside the thylakoid, inside the grana. So these protons that store a lot of energy, they store a lot of potential energy, will now diffuse down concentration gradient through this ATP synthase. So ATP synthase is not only a protein nor an enzyme, but it is also a channel for the hydrogen ion diffusion. It is a protein channel that is hydrophilic from inside and that will allow these protons that have been pumped extensively to the inside of the grana to the extent that they are now having a much higher concentration inside than outside. So once they find a channel for them, they will diffuse down concentration gradient from the inside of the grana or the thylakoid to the stroma of the chloroplast or to the outside. Of course, this is a kind of facilitated diffusion since we are using a channel which is ATP synthase. So it is this step that allows the formation of ATP, because it is this step that allows the protons to release the stored energy. And it is at this step that we are allowed to convert ADP to ATP. So when we said previously that the electron transport chain gives you energy, and that this energy is used to pump protons and to generate ATP, actually, we shouldn't write this as two branches, but we should say that proton pumping occurs first, and that this proton pumping will store potential energy, will do two things, actually. It will store I'll say it again. So it's the pen again. So actually, we have proton pumping, So we have energy that is released from the electron transport chain, and this energy is used to pump protons. And while pumping protons, we are doing two things. We are storing potential energy in these protons, and we are creating a gradient for diffusion, okay? And this gradient for facilitated diffusion is what we call the proton motive force. So how did we have this motive force of the protons that allows them to diffuse by facilitated diffusion down concentration gradient? We obtained it because we had previously accumulated the protons inside. Let's go back to this diagram, which is the same as the one before, but with a bit more details. First of all, as you see, we have light that falls on photosystem 2. And at the bottom here, we have oxygen. Where does this oxygen come from? From photolysis. Where does this oxygen go? It is released outside the chloroplast and then released outside the cell, the plant cell, through the stoma. So it is the main source of oxygen for breathing by living organisms. And then the rest of the water molecule gives us protons. So as we said before, part of the protons inside, part of these protons is due to photolysis, but the rest of the protons is due to proton pumping. And these protons that have been pumped store a lot of potential energy. These protons whereas the protons that result from just splitting of the water molecules do not store that energy. And then the electrons are transferred along the electron transport molecule. So we have quinone first, and then we have a series of enzymes and electron carriers that are called the cytochromes, and we have plastoquinone, this is plastoquinone. And then, as you see, there is pumping of protons using the energy that is released from electron transfer at gradually decreasing levels. And it is important every time you talk about proton pumping to mention that the protons are being pumped from the stroma of the chloroplast to the inside of the thylakoid. This is the inside of the grana. Why do they say the cytoplasm of the prokaryote? They are just referring here to the theory of endosymbiosis, where they consider that the chloroplast is a prokaryote that has been introduced into another prokaryote. So this is the cytosol of the prokaryote, and then we enter into the stroma of the chloroplast, and then we enter inside the thylakoid. Here again, you can see that copper, for example, is a cofactor for the enzyme. You can see that the second electron transfer chain will give rise to reduced NADP, but that ATP, although formed by the energy resulting from photosystem 2 electron transfer, yet it is formed only when it reaches the ATP synthase. So ATP, it stores what? It stores the energy released by the electron transport chain of photosystem 2, right? Yet it is formed only here when the protons are pumped via, when the protons have enough electromotive force or proton motive force to diffuse by facilitated diffusion down concentration gradient through the rotator bulb of this enzyme. See that the head of the enzyme is always directed towards the stroma. And in case of the mitochondrion in cellular respiration, it was directed towards the inside of the mitochondrion, which is the matrix. So it's either towards the stroma of the chloroplast, that is outwards in the cytosol, or it is towards the matrix of the mitochondrion, which is the inside of the mitochondrion. But it's always towards the jelly-like substance, okay? Here again, we have the same, we have light that falls on photosystem 2, and then you have more details concerning the primary acceptor first, and then the transfer of electrons along the transfer of electrons along the electron transport chain, and then the same occurs in photosystem 1 and the formation of reduced NADP. Here we refer to the term chemiosmosis. They say energy for synthesis of ATP by chemiosmosis. Actually, chemiosmosis refers to the transfer of the protons down concentration gradient along the ATP synthase. So this process of diffusion of the hydrogen ions down concentration gradient is called chemiosmosis. We have talked about chemiosmosis before. Chemiosmosis is the movement of ions across a semi-permeable membrane down the electrical gradient. Did they move down a semi-permeable membrane? Yes, they did, because they moved across the ATP synthase, which is present in the cell membrane. And here we tell you the story again from the beginning. In this slide, this is a wrap-up of what I've just said. So photolysis occurring in the thylakoid creates a buildup of hydrogen ions inside the thylakoid. But we have another source for building up of protons inside the thylakoid, which is the pumping. So we have another source of protons here, which is the active pumping, okay, other than photolysis. These hydrogen ions will diffuse passively, as we said, across the enzyme to reach the stroma. And once in the stroma, they will be actively pumped. And this is very important, that we have here like a cycle for the protons, meaning that you might be wondering, you might have wondered here when I talked about pumping of these protons to the inside, about the source of these protons. Where did they come from? Actually, they are part of the protons that pass through the ATP synthase. So it's like a cycle. So that's why we have postponed talking about pumping. So once reaching the stroma inside, they will be, once reaching the stroma outside, the stroma is outside, they will be actively pumped inside or inward by the cytochromes in the thylakoid membrane to the inside of the chloroplast, using this energy that has been released through the electron transport. And why has the energy been released along electron transport? Because the electrons are passed down, are passed from one cytochrome or one electron carrier to another at gradually decreasing levels. The hydrogen ions that are pumped will store a lot of potential energy. It is the energy that has been used to pump them, and that energy will be released once again by passing across the ATP synthase, and this released energy will be stored in ATP and so on. Now, what we have talked about is non-cyclic photophosphorylation, but now we are going to talk about cyclic photophosphorylation. In cyclic photophosphorylation, we start as usual by solar energy that drops on a photosystem. So photons fall on photosystem 700, and the electrons are excited and they are accepted by a primary electron acceptor. But after having been accepted by the primary electron acceptor of photosystem 1, these electrons will not continue in the electron transport chain of this photosystem 700 or this photosystem 1. They will be transferred from ferredoxin to they will be short-circuited, if you want, to the electron transport chain and the cytochrome complex of the photosystem 2 and back to photosystem 1 once again. So what is actually working is the electron transport chain of photosystem 2 that is responsible for ATP formation, whereas the electron transport chain of photosystem 1 that is supposed to form reduced NADP is short-circuited. We bypassed it, so we prevented it from forming reduced NADP, and this is what we're going to read on the slides and see in the comparison in the diagram. But let's first know why cyclic photophosphorylation occurs. First of all, why is it cyclic? Because as you see in this diagram, every time we return to the same point, which is the reaction center of photosystem 700. So it is cyclic. That's why it is called cyclic photophosphorylation. Again, it is phosphorylation because we have formed ATP. So we have formed ATP. It is a cyclic process. No reduced NADP has been formed. If we ever ask you, why are we producing ATP here? Why did we succeed to produce ATP here? Because the electron transfer chain of photosystem 2 is on. But why didn't we form reduced NADP? Because the electron transfer chain of photosystem 700 or photosystem 1 is off. And why is the electron transfer chain of photosystem 700 off? Because it has been bypassed. Because it has been bypassed. And this bypass is the cause we didn't produce reduced NADP. Okay? So in cyclic photophosphorylation, actually, it's a cyclic process because we return to the same point every time. And it is phosphorylation because we produce ATP. And all the energy generated will be utilized to produce ATP. No reduced NADPH is formed and no oxygen is released. No oxygen is released. So what happens actually is that, or the reason behind the cyclic photophosphorylation is that actually in the dark reactions, we consume a lot of ATP. We consume ATP more than the ATP that is provided to this biochemical pathway in the light-independent reactions or the dark, previously called dark reactions. So every now and then, the plant cell finds itself in a status of shortage of ATP. It runs low on ATP, so it has to stop and it has to carry out cyclic photophosphorylation to replenish the ATP level. So actually, as I've just explained, there is a cyclic electron flow. So the photoexcited electrons are taken on a short circuit pathway or are short circuited. So they travel from the electron transport chain of photosystem 2 to photosystem 700. And then, as we said before, to an electron acceptor, and then to the cytochrome complex in the photosystem 680 transport chain. Do they have to pass to photosystem 680 and along its transport chain? Yes, of course, in order to be able to form ATP. So we are actually bypassing the electron transport chain of photosystem 700 or photosystem. So in non-cyclic photophosphorylation, we always have photolysis. And if we have photolysis, this simply means that oxygen is liberated. But in cyclic photophosphorylation, no photolysis of water occurs. So there is no oxygen liberated. In non-cyclic photophosphorylation, both, of course, as you know, photosystem 2, we should mention this first, photosystem 2 and photosystem 1 work and are involved. And there is no cycling of electrons, and both ATP and reduced NADP are produced. Whereas in case of cyclic photophosphorylation, it is only photosystem 1 or photosystem 700 nanometers that's involved, and the electrons that are released by photosystem 700 will return to it from the electron transfer chain of photosystem 680 after having bypassed its electron transport chain. And what is important is that the cell is focusing on only one sole purpose, which is this is the sole purpose, but the sole purpose not forever, but for the time being. It is what is the time being? We are in a status of shortage of ATP. So cyclic photophosphorylation is a temporary process. It's not a major process, and it will stop once the ATP stores are replenished. It will stop once the ATP stores are replenished. So these are the major differences between cyclic photophosphorylation and non-cyclic photophosphorylation, and this is the diagram that represents cyclic photophosphorylation. Again, here, as you see, you have photosystem 1 or photosystem 700 that traps solar energy, and that where electrons in the center of the molecule get excited, and they are received by an electron acceptor, and that electron acceptor will give its electrons to ferredoxin, but very soon we will have a short circuit and reach the electron transport chain of photosystem 680, which is the one responsible for formation of ATP molecules. Thank you, and see you in the next video.